A new breed of aircraft is outperforming the 850-passenger double-decker A380 and the 660-passenger humped 747, causing a revolution in the airline business. Since air travel has developed to meet the needs of passengers, both the industry and the passengers gain from this development. The $30 billion wager, the 787 Dreamliner, completely changed the airline business and the way that planes would be constructed going forward. Boeing threw caution to the wind and invested $30 billion in the 787, the first commercial aircraft primarily constructed of composite materials such as carbon fiber reinforced polymers. Because of its strength and flexibility, the 787 is the first commercial aircraft in its class, and the first airplane built entirely of carbon-reinforced plastic. Up to 5 times stronger and 1/5 as heavy as steel, carbon-reinforced polymers are extraordinarily durable. They are able to bend, flex, and split readily, so they are unable to form a solid portion on their own. They must be joined with a plastic resin to create a solid substance. Boeing creates the fuselage by wrapping a carbon fiber tape soaked with plastic resin around a rotating fuselage mold. This automated tape-laying process allows Boeing to build large airplane parts. Building a bespoke oven big enough to fit the item using this production method costs a lot of money up front, but the advantages are well worth it. The Boeing 787 is an effective long-range aircraft that can open up new routes thanks to its larger windows, stronger fuselage, and carbon fiber construction. By increasing internal air pressure by 7.3% and 25% lower in altitude, respectively, the fuselage improves comfort and minimizes farting during the flight. The large windows prevent tension from building up around window borders, and the carbon fiber structure does away with the necessity for joints and bolts to bring pieces together. Carbon fiber shins are another item that may be utilized with the 787 to repeatedly kick Dustin Poirier's kneecap. During flight, the carbon fiber composite wing spars withstand upward bending stresses. The primary load-bearing structure and fuel storage box are constructed by the forward and rear wing spars with ribs, which together make up the wing box. The 787's wings have a 3-meter vertical movement capability, meaning that for 3 seconds during flight, the aircraft must support 150% of its maximum anticipated load. A greater aspect ratio wing was produced by engineers. This is the ratio of the wingspan to the mean chord, or wing width. The huge aspect ratio of the 787 is 11, which causes the wings to bend significantly when in flight. Gliders, which prioritize reducing energy wasted to drag, have the highest aspect ratio wings. This allows them to fly in the air for longer periods of time without using an engine. These aircraft usually have aspect ratios higher than 30, and their vortex drag penalty is the lowest. Unpowered gliders are not affected by the lower internal volumes of wings with a higher aspect ratio. However, a smaller interior volume translates into a shorter range for aircraft that require fuel storage space. Supercritical aerofoils, which have a greater thickness to chord ratio and a blunter leading edge to increase interior volume, are a novel type of aerofoil used in the 787. In order to solve the low internal volume issue related to high aspect ratio, NASA created the supercritical wing. The wing's design philosophy is similar to that of the 787, and it was initially tested on a modified TF-8A Crusader. The purpose of the supercritical wing is to postpone the production of shock waves across wings, which can reduce lift and induce wave drag. There is a drop in pressure at the top of the supercritical wing because of the flat top, which prevents the air from accelerating as quickly as it would over a traditional aerofoil. The supercritical aerofoil's concave curve beneath the wing increases pressure there while leaving the critical Mach number unchanged in order to make up for it. The bigger leading edge and radius of Boeing's 787 aircraft boost lift and postpone flow separation. As the wing travels, the aerofoil shape continuously changes with computer-calculated precision. To customize stiffness, engineers laid down the skin on a mold using composite materials and automated tape. The fibers were arranged in a certain manner. This guarantees that, as it increases in speed, the wing will deform just as the engineers intended. In aeronautical engineering, aeroelastic tailoring is essential because it enables wings to alter shape in flight to accommodate varying speeds. With the use of Boeing's hybrid laminar flow control technology, turbulent flow generation may be delayed and controlled, perhaps saving up to 30% on fuel consumption. NASA and Boeing looked on a 757 suction system in the late 1980s and early 1990s that would pull in boundary layer air, a layer of sluggish air that adheres to the surface of moving objects. The inner and outer skins were joined to a complex plumbing system that was connected to a turbopump that drew air from the air's boundary layer. By delaying and lessening the magnitude of turbulent flow, this technology could lower the plane's drag. This ducting system is located inside the 787's horizontal and vertical tails, not between the wings. 15% of the aircraft is made of titanium, a pricey material that resists corrosion when in direct contact with carbon fiber composites. Similar to metal's kryptonite, carbon fiber causes aluminum to rust and disintegrate. When two materials come into contact with an electrolyte, such as salt water, that has varying electric potentials or nobilities, galvanic corrosion takes place. Graphite is on the far right, and aluminum is on the far left, signifying that they are noble materials. When they exchange electrons and ions, the anode is consumed. This is worse when the surface area is greater. Engineers selected a material that was closer to carbon in the galvanic series in order to prevent galvanic corrosion. Boeing replaced the titanium frame surrounding the cockpit windows with aluminum that has been specially coated to resist corrosion, saving production costs and removing titanium components. A purchase-to-fly ratio is used by manufacturers to measure this waste, which is a major cause of higher manufacturing costs. To solve this problem, Boeing has partnered with Norsk Titanium, a titanium 3D printing business. It is difficult to 3D print metal parts since most titanium 3D printing requires melting powdered titanium combined with lasers. When the process was shown using high-speed X-ray imaging, the researchers discovered a number of flaws, including different heights, blasted powder, and bubbles that caused pores in the metal. Micro-imperfections in 3D printed objects frequently result in fatigue and crack formation, reducing their lifespan. Norsk has created a proprietary wire-based metallic 3D printing technology for titanium that is 5,100 times faster than powdered printing and uses 25–50% less titanium overall. The first 3D printed structural parts approved by the FAA were produced using this technology, and they were used in the Boeing 787's first flight. Because composite materials are poor conductors, Boeing also eliminated copper from their wing design in order to reduce costs. Between 1950 and 1975, lightning strikes happened once every 3,000 hours of flight time. Resistive heating caused 42–46 holes in the fuselage. To guarantee such a disaster never occurs again, the aviation industry has put in place stringent safety protocols and conducted tests for lightning protection. Copper strips were used in the design of the early 787 wings to guard against resistive heating damage to the composite structure. To remove possible spark spots, fasteners were sealed with an insulating substance, fitted with compression rings, and sealed with a sealant. The 787 aircraft uses nitrogen inerting for ignition, requiring oxygen. However, the company eliminated copper mesh and insulating caps as cost-cutting measures. Instead, aluminum or other metals were used for the tail cone, engine cowling, and leading edges of the wings and tail. Aluminum leading edges are heat conductive and advantageous for de-icing. The 787's wings are kept warm using electrically heated blankets affixed to the slats, which reduces drag and energy loss. This innovative design reduces drag and energy loss, making it the most efficient long-haul aircraft ever created. The 787 was the first commercial aircraft to eliminate the bleed air system, requiring a new engine and a thorough redesign of multiple systems. The 787 is the most efficient long-haul aircraft ever created due to its cutting-edge jet engine and system architecture. Thank you for watching this video.